7.6 Trigonometric Equations. So this will be the last section that we're going to go over in Chapter 7, like I was saying earlier. There is a 7.7, but it's unimportant. We won't be going over that one. So we'll go straight into the solving of equations. For this particular one, there's quite a bit of stuff that we're not going to cover. So we're not even doing all of 7.6. We're going to cover up to where it says trigonometric identity substitutions. So from here on out, after this, these are going to get cut out. So those I won't give you homework over or anything like that. So we'll start off with linear methods. Example number 1. So for example 1, we solve the equation. It says 3 tangent theta minus square root of 3 equals to 0, part A, over only this interval from 0 through 360, so that's the fundamental circle. And then for all solutions, which means all circles outside and including the fundamental circle. So not just between 0 and 2 pi or 0 and 360, but for any angle from negative infinity to positive infinity. So that allows for multiple rotations. So that keeps on going forever one way or forever the other way. Okay, so we'll try to figure out part A first, and then we'll try to figure out what they mean by part B, and if we can come up with a nice little concise way of representing those types of solutions. So for part A, over the interval of 0 to 360, so I need to actually manipulate this equation first off. So the goal is to solve this equation. So that's 3 tangent theta minus square root of 3 is equal to 0 is the equation that we're trying to solve. So the goal is to solve this particular equation. And we solve it like any other equation. The only thing here is that instead of theta that we want to solve for, the idea first is to isolate tangent of theta. So that's what I'd like to isolate. So we treat this as any other equation. This is a linear equation, by the way. Linear in tangent theta, not linear in theta. It's nonlinear in theta. So we just treat tangent theta as the variable. You're going to add square root of 3 on both sides. So 3 tangent theta. So then this ends up just becoming 3 tangent theta is equal to positive square root of 3 if we add square root of 3 on both sides. Next step, you divide by 3 on both sides, and we've successfully isolated tangent of theta, which is equal to square root of 3 divided by 3. So there's our solution, or what's it called? There's a solution for tangent of theta. So this is the process for solving for tangent of theta. This is the very first step in any equation like this. So do what you normally do, or do what you normally know how to do when solving an equation, and isolate any of the circular functions that you see. In this case, we only saw tangent theta as a circular function. So what we're going to do next is we're going to analyze this particular solution, or this equation. So we have the equation written this way: tangent of theta is equal to square root of 3 over 3, and we'd like to analyze this a little bit. So I think we saw this example in the previous section 7.5. So if tangent of theta is equal to square root of 3 over 3, and if we had a sine and a cosine, or an x and a y coordinate on a unit circle, then this came from us first off, at the very last, rationalizing the square root of 3 underneath a 1. So 1 over the square root of 3. And that came about after reducing this complex fraction, 1/2 over square root of 3 over 2. And those 2's cancel out by, if you remember, law of the sandwich. And that was in 7.1 through 7.4. So 1/2 came from sine of, and we should remember, 30 degrees. And square root of 3 over 2 came from cosine of the same 30 degrees. Because tangent is sine over cosine. So there's a solution. Not all solutions, but there's one solution. So theta equals to 30 degrees is definitely going to be one of my solutions. So that's going to get saved for part A. So what I'm going to do is I'm going to graph that 30 degrees somewhere here. So that is where tangent, that's one of the places where tangent theta is equal to square root of 3 over 3. That's not the only place, because tangent is positive in the first quadrant. It's also positive in the third quadrant. It's negative in the second and in the fourth quadrants. So I'm not going to have any more solutions in the second or the fourth quadrant, so there's not going to be nothing in here, there's going to be nothing in here, but there should be another one in the third quadrant. So shortcut, where it's going to be in the third quadrant would be exactly 30 degrees away from the x-axis as well. So if this angle was 30 degrees away from the x-axis, this other angle should be the same, 30 degrees away from the x-axis. That's called a reference angle. So tangent of theta is going to have the same value by the same reference angle in whichever quadrant you're talking about. And remember, reference angles are measured off of the x-axis always. So then that means this here is 30 degrees. And if that's 30 degrees, that's coming from a full angle of how much? 210 degrees, I believe. So I used that 30, added it to the 180 to get that 210. So there's my second answer, 210. And that's going to be the answer for part A. That is everything they wanted for part A, because those are the only two places I'm guaranteed on the circle between 0 and 360 that tangent's going to equal to square root of 3 over 3. So that solves part A. So I'm minded to stop here and move on to the next example and not cover the all solutions one, but the all solutions one is not too bad. So that one's not that bad. So let's see. How does that look? So basically, if we're looking for all solutions, we definitely must have 30 and 210. For sure, for sure. So let's see if we can find more. So on the fundamental circle between 0 and 360, that's all we have. But we can continue going outside of the circle and find another one. This one. And that's a full angle of how much if I were to track it all the way through. So y'all notice that's a positive angle that's bigger than 360, and that angle is 360 plus 30, which is 390 if I do the math right. So 390 is the next one. That's the next one that gets added on here. And we keep on going. If I keep on going to where this line happens again, that's an extra how many degrees from there? You're going to notice it's going to be 180 degrees off. So from here to here, it's an extra 180 degrees. It's a half circle. So that's a straight line. It cuts that circle in half. So there's 180 degrees in between solutions. So what you do is you take that 390, and I'm going to add 180 to it. And I got to do this by piece, so that's 0. This would be 7, carry the 1, it's going to be a 570. So 570 degrees. I have a calculator, but I'm not going to use it yet. I'm only going to use it for the heavy lifting stuff. And that's going to be for inverse tangent, inverse cosine, inverse sine of weird angles or weird values. And we can keep on going. So 570 plus, I'm going to put a bunch of dots here. And I'm neglecting something here. I'm neglecting the left-hand side if I'm going the other way. So let me erase all this red stuff if I can. Hopefully I'm able to. So what if we wanted to go the other way? See if I can erase. And there's some red stuff I can't erase. So what if I wanted to go backwards this way to this angle right here? What would that angle be? So it's negative 180 degrees except for this 30 degree mark that it's not completing. So from 180, this would be what? Negative 150. We're subtracting 30 from 180 and you get 150. So that's an angle of negative 150. So before 30 degrees, there's a negative value of 150 degrees, so negative 150. You keep on going though, you find the next one, and the next one is, what would that be? Negative 330 degrees. And where am I getting that from? It's almost a full 360 backwards except for 30 degrees, so 360 minus 30 would be 330. And then you keep on going. You add another 180 to the 330 with a negative sign in front of it, of course, so you subtract. And then you keep on going. So I'm going to put a dot on that one too. So here's the idea. So there's a bunch of them. That's not all of them, but that's a lot more than what we had in the first part, part A. So this isn't all of them, but if you notice, the difference between all of these, if I were to line these up, so and I'm going to try to line these up. Let me move this over this way, and I'm going to include this before the 30 this way. And that's probably not the best way to do that. So it was negative 150 degrees, negative 330, I think, and then dot, dot, dot this way backwards. So there's a ellipses, which is the dot, dot, dot. That's the formal name for three dots to say that it keeps on going. So that those are ellipses. There's ellipses on either side, on the left and on the right. And that's because we can keep on adding 180 degrees over and over and over, or subtracting 180 degrees over and over and over. And every time you do that, as long as you start at 30 degrees, you're always going to land on one of the solutions here on the circle. So it's going to be on that line that has a 30-degree reference angle in the first and the third quadrant. So it's forwards or backwards, 180 degrees, starting at 30. So 30 is your starting point, so that's important. So let me draw in black. So then there's a way that we can do this. So if you remember, we expressed asymptotes for tangent, cotangent, secant, cosecant. It was in radians, but we expressed them as an infinite expression that kept on adding or subtracting multiples of a period or multiples of a asymptote interval. So same idea here. I'm going to say that, well, the main one is at 30 degrees. And all we got to do to find another one is to add a multiple of 180 degrees. So it's 30 degrees plus, or it's minus any multiple of 180 degrees. So you could put a plus or a minus on that if you understand n is a positive integer or 0. Or you could just take away the negative and you could just let n represent anything 0, plus or minus 1, plus or minus 2, plus or minus 3. And then ellipses and so on. There's my closed form solution for theta. And those are all theta values that solve the same equation, 3 tangent theta minus square root of 3 is equal to 0. So that's for all solutions. So if they ask for all solutions, they want this, plus an n times something, whatever that something is. And that's it for example 1. So what are the major parts of this? So because there's quite a bit here that can allow us to get confused. Your very first step is to solve as if this were just a regular algebra 1 equation. The second is to try to figure out what's one of the values of theta that solves. So you're trying to find any. You're grasping at straws pretty much. You're trying to guess for any theta values that solve this equation. So any solutions I can find, we look for it. Now that's a nice unit circle value, so we can find, or we found easily that 30 degrees was one of those values. That's because we know the unit circle very, very well. So 30 degrees, we drew it. And then using that unit circle that I have propped up here, we found more. So there's only 2 if this is a linear equation. The reason being, tangent theta is equal to a value. There's going to be 2 places where that happens. If it's positive, it happens in quadrants 1 or 3 for tangent. If it's negative, it happens in quadrants 2 or 4. That's why there's always 2, because tangent repeats itself twice in the full circle. That's the reason why. So there's always going to be 2 there. And then what else? Then we extended by finding out the distance between those 2. The distance between those 2 is 180 degrees. So that means if I want to find any more than just those 2, I can add or subtract 180 degrees from either one of those 2, and however many times, and I should be able to find more solutions. So understanding that pattern, we were able to write it using this expression. Theta is equal to 30 degrees plus any multiple of 180 degrees, any integer multiple of 180 degrees. So where does this get more complicated? Several ways. This linear equation could get a little uglier, and the way that we can make it uglier is by making it a quadratic equation, or by having different functions, not just tangent. What if we had tangent and secant? Then I'd have to probably collect one of those and write it in terms of the other using an identity. Or if it's strictly quadratic and there's only one function, I might have to use some extra method, some tougher methods or more complicated methods for solving equations like quadratic formula, completing the square, factoring, stuff like that. Where else could this get crazy? In the analyzation portion, maybe I don't know what the value of theta is, and in that case you go to a calculator and you apply an inverse tangent to both sides to solve for what theta is going to equal to, or to find one value that's equal to theta. So we'll try some more. Example 2. So this is going to make the equation a little tougher. We're going to use the zero factor property method. Zero factor property method applies when the equations are factorable. So they have a higher order terms, but they're factorable. So that's one step above the one that we just did. So we're solving cosine cotangent equals to negative cosine over the interval 0 through 360. So the first step is you solve the equation and try your best to solve it. So I'm going to zoom in on this. Cosine theta times cotangent theta, and this is a multiplication sign, so just a little dot for multiplication, equals negative cosine theta. So when you're solving this thing, so here's the solving process. There's always a temptation to just cancel out what's common on both sides. If you're canceling out expressions that are functions of the variable, or just the variables themselves, you're going to run into some problems. So I can't simply just cancel those two out. They don't cancel. Now the reason why they don't cancel is because those carry important information. There's values of theta that solve that piece of the puzzle, and you don't want to cancel them out. So what you're going to end up doing is, well, in this case, I can't isolate the two functions. I might want to just try leaving them all on one side. So I'm going to move this cosine theta over to the side. If I do that, these become 0, and we're left with cosine theta, cotangent theta, plus cosine theta, and that's going to equal to 0. Okay, so why did I do that? I wasn't able to cancel them out, so might as well move them over to the other side. Now, if you can notice that on either side of the equation here, if you were able to cancel out the cosines by division, then what that translates to is if you move that over to the other side so that way they're all together, you can factor out what's common. That means they're going to be common in both terms. So we have a cosine that's common in both of those two terms. Let's factor it out. This is the correct way to deal with common factors on left or right hand sides. Move everything to one side, factor out what's common. Don't divide it out, factor it out. Cosine, in parentheses, what's left over, and what's left over is cotangent theta plus 1 equals to 0. And now what we've done is we've successfully separated the two functions. This was a separable equation, cosine separated from cotangent now, and separated by factors. And if that's the case, we've separated them into two factors equal to 0. In essence, we have two numbers that are multiplying to each other that are equal to 0 when you multiply them. That only happens when either of those two factors individually, cosine theta is equal to 0, or the other situation or possibility, cotangent plus 1 is equal to 0, and you solve both separately. Cosine of theta is equal to 0 has its own set of solutions, so what I'm going to do is I'm going to go back to a circle if I have one, and yes I do. So I'm going to zoom this thing back out, and I'm going to move these over here. Actually, I'm not going to move those over there. I'm just going to copy them over here in a different color. So let me do each of them in a different color. Cosine theta is equal to 0, and then in blue, cotangent theta plus 1 is equal to 0. In essence, that's cotangent theta equals negative 1. Let me rewrite that. Cotangent theta is equal to negative 1. Okay. So in blue or in red, so I think in red, we'll start with the cosine first. Cosine theta is equal to 0. And if you remember, cosine is the x-coordinate. So we want all values, theta, that make the x-coordinate equal to 0. So that would be here and here, if you notice what those coordinates look like, 0, 1, and 0 and negative 1. Those are the only two places on the fundamental circle, 0 to 360, for which cosine is 0. So I'm going to record both of those angles. So there's this one, and that's at 3 pi over 2. Actually, I don't have to record it because they're already there. And then pi over 2. So let me draw them. And then this one. And this one looks like this. So we already have two solutions. Pi over 2, 3 pi over 2. And I can go ahead and box those or record them over here to the side. So right away, this one gave me theta equals to pi over 2, and 3 pi over 2. This one should contribute a few more as well, and I'm expecting 2 that it's going to contribute. Cotangent equals -1, and I might want to use a more complicated strategy for that. And what's the strategy that I need? If you remember, cotangent is equal to 1 over tangent, and that's supposed to equal to -1. So if that's the case, if you cross multiply, you get tangent theta equals -1 also. And maybe we're more comfortable with thinking of tangent of theta equaling to -1. Now tangent of theta is equal to -1 when sine over cosine equals to -1. Sine over cosine equals to -1 means they have the same exact value, the same absolute value, but one of them differs in sign. So it's either positive or negative square root of 2 over 2 on top, or a negative or a positive square root of 2 over 2 on top. They have different signs, which is why I have a plus minus on top and then a minus plus in the bottom to say that they have different signs. So this happens when sine and cosine are square root of 2 over 2, except for a negative sign. So they differ by a negative sign. And that happens, tangent is negative in which quadrants again? Quadrants 2 and 4. Those are supposed to be straight lines, so just pretend those are straight lines. So that's going to be this angle, and then this angle. That already looks a little messy. But we got to figure out what those angles are. So that's a 45-degree reference angle. 45 degrees has a pi over 4 structure to it. So this one here is a 3 pi over 4. This one here, if you remember, it's 7 pi over 4. This one here is a 1 pi over 4. This is a 5 pi over 4. So it's 1, 3, 5, 7. And I'm not using those because those would be wrong. Because that's where tangent's positive and cotangent's also positive. So I want it in the second and the fourth quadrant. And those are my only other two answers. So I'm going to go ahead and include those in here for boxing. So it was 3 pi over 4 and 7 pi over 4. And those are it. Maybe I should explain just a little bit more why that's it. So if I reread the problem, solve this equation over the interval between 0 and 360. So we don't want all values of theta. We just want the ones between 0 and 360, the fundamental circle, or the primary circle, or the primitive circle, or whatever you want to call it. So just the main circle. And these are our only possibilities. That's example 2. So the next few, so here I didn't have to use a calculator, but in the next few examples, let's see what we have. We have example 3, which is going to have us use the, that's zero factor property. So that one's factoring again. So they tell you what it is you're going to use. Zero factor property. This one says quadratic formula. So a lot of the times if you're having to use the quadratic formula, that's where the calculator is going to step in for solving for theta. That's example 4. And then the very, very last one we're going to go over is example 5, and that's going to be it. This one is by squaring. This is a technique we haven't seen since chapter 1. So we'll go over those in a bit. So example 3. Solve 3 sine squared minus sine x minus 2 equals to 0 over the interval 0 to 2 pi. Notice how they changed the format. This is in radians now and not in degrees anymore. So we're going to have to go back to radians, not degrees. Oh, and by the way, that reminds me. So I didn't give the answer in the correct format. This was in degrees. So if this is in degrees, you better write your answers in degrees. So this is wrong. I'm not boxing this. Or I'm not good to box that. So what was this? Why did I write that in radians? I wrote that in radians first because I didn't read the whole problem at the beginning. So that causes a lot of problems when you don't read a problem all the way through. And the other reason, I'm more comfortable with radians, in my personal opinion. Or that's just me. I'm a lot more comfortable with radians than I am with degrees. As weird as that might seem, later on, radians becomes the more convenient way to do things. In this course, we're just being introduced to radians, so that might not be the case for you, but it's definitely the case for me. But let's see. So I'm supposed to change these so that way they're in degrees. So that's 90 degrees, 270 degrees, 135 degrees, and then 315 degrees. I mean, I'm comfortable with both. So those are easy to memorize. Those are all unit circle values, so I don't expect you to have a lot of trouble going back and forth between these two. Now, where it gets a little uglier would be maybe for examples 4 and 5. But example 3 should be an easy one too. Hopefully, we'll see. So 3 sine squared x minus sine x minus 2 equals to 0. So our first step, solve this equation. 3 sine squared x minus sine x minus 2 is equal to 0. And what we do is we make a substitution. I'm going to say that this is 3y squared minus y minus 2 is equal to 0. And that these two are exactly the same thing if y equals to what? Sine x. That's my transformation. I'm not going to box it all the way through because that's not an answer. So that's the method that I used to rewrite this equation without trigonometric functions. So now it's just a y variable. So if that's the case, this thing should be factorizable, hopefully, because they're telling me to use a zero factor property, so that implies that it's going to be factorable. So if I try factoring, we're not going to fail at it, hopefully. The way that we do this, the old school way, is you take the coefficient 3, you take the last coefficient, so the first coefficient, leading coefficient, and you take the constant term, negative 2, which, by the way, a lot of you guys were freaking out in both SAT days. What's a constant? This is a constant. Numbers with no variables. So you take the constant term, which is negative 2, and you want two things, two conditions this has to satisfy. When you multiply 3 and 2, and then when you add 3 and 2. When you multiply 3 and negative 2, you get negative 6. But when you add 3 and negative 2, you get positive 1. So we want two numbers, and we're going to erase these two numbers. We want two numbers that basically do the same thing. So we're supposed to get, and it's supposed to be negative 1, my bad. So negative 1. And where am I getting that negative 1 from? That negative 1 is this middle coefficient, negative 1. So we want two numbers that multiply to negative 6, but add up to negative 1. So we got to figure that out. What numbers would that be? I got to think about that. I don't know why I have to think about this for so long. I'm supposed to be really good at this. So 3 and 6 definitely. And let's write 3, or not 3 and 6. 3 and 2 definitely, because 3 times 2 is 6. Now I want a negative 6 when I multiply them, so one of those two have to be negative. But I also want a negative 1 when I add them, so that's going to be a negative 3. And let's just double check. Negative 3 times 2 is negative 6. Negative 3 plus 2 is negative 1. So yeah, this works. Negative 3, positive 2. So what we do is we take 3y squared, copy it down, and then we expand the middle term. The negative y is going to change to negative 3y plus 2y. And then minus 2 gets dropped down, equals to 0. So what that does is it incorporates these two special numbers that we just came up with, and we use those two numbers as coefficients on the y term, and we split them up. And the reason why we split them up is because I'd like to factor these two, and then I'd like to factor these two separately to see if I can come up with a nice simplification. That's going to be what, 3y on the outside, y minus 1 on the inside, plus there's a common 2 on the outside, y minus 1 on the inside. And if you did this right and found those numbers correctly, these two should match, and they do. So what we do is we factor that out, y minus 1. What's left over is the 3y plus 2. That's equal to 0, and there you go. There's a foolproof way of factoring this type of expression. What we do is we solve for y now. This implies that y must equal to 1 and negative 2/3. Now I'm not really trying to explain where I got those numbers from. I'm already explaining quite a bit. This is all Algebra 1, Algebra 2 stuff. So we should know where we got y is equal to 1 and y is equal to negative 2/3. And what we do is we take the substitution equation, plug that stuff back in for y. So what this implies is that sine x equals to 1 and sine x is equal to negative 2/3. Neither of these are going to have no solution. Both of these contribute solutions. So we look at these one by one. Where is sine 1? So don't forget, sine is the y-coordinate on the unit circle. So I'm looking for all angles theta that make sine theta equal to 1. And I think there's only one of those. This is one of those weird cases where there's only one. So when the y-coordinate's 1, in no other place is the y-coordinate equal to 1. And what angle is that? That angle is pi over 2. So I'm going to erase that. I circled the pi over 2 that's up there. So there's one of my answers. This one told me that x must equal to pi over 2, for sure. That's one of my answers. This one here, negative 2/3. Negative 2/3, by the way, is inside of the interval negative 1 to 1. So sine has a solution. Sine x equals to negative 2/3 should have a solution, and I believe it's going to have two solutions. So I'm expecting two numbers that make that true. So let me write that over here. Where is sine x equal to negative 2/3? So what you do is you remember that that's a y-coordinate. Sine is a y-coordinate. You're looking at where on the circle do I have a y-coordinate equal to negative 2/3. So y-coordinate negative 2/3. Let's say negative 2/3 is here, right? Because let's say this is negative 1/3, negative 2/3, and then negative 3/3. So negative 1/3, negative 2/3, and then negative a whole down here. So negative 2/3 is here, and what you do is you draw a line through there. Because it's a y-coordinate, you draw a horizontal line. Because you want y to equal to that number. Y equals to a number is a horizontal line. So you draw a horizontal line, and that's kind of drawn poorly. You draw a horizontal line, and a horizontal line like this should cross the circle twice. So what we want are these two angles. That's kind of weird. So my lines come out squiggly, and I don't understand why. Maybe the thing that I'm writing on, the screen, is kind of wavy, and I have no idea. Or maybe I'm just really bad at drawing lines. But either way, we have this angle, and then we have this angle. So those are my two angles that we have to solve for. And once we solve for those, since we're only doing this between 0 and 2 pi, we're done. Because that's the principal circle, or the primary circle, fundamental circle, main circle, whatever. So how do I get that done? What I want to do is I want to find the value of x that makes sine x equal to negative 2/3. And I'm going to go to a calculator for that. So on a calculator, x is supposed to equal to whatever we get when we plug in inverse sine of the ratio negative 2/3. So the ratio is negative 2/3 is what you're going to plug into inverse sine. How to use your calculator for the inverse sine of negative 2/3. So first off, you want to make sure that you are in radians, because this is asking for values in radians. And to do this in radians, you would press the on button to get to the screen. You're going to change your document settings number 5, so you'll type in the number 5, and that's going to pull up this menu. Document settings number 2, so you type in 2, and that's going to take you to this menu. Mine's already in radians. If you're working with the fresh restart, it's going to be in radians by default. So I'll press OK. And I'm going to work within a document environment, not a scratch pad environment. So my document, I'm going to start a new, I'm going to go to my current document number 4. My current document's in radians. And I'm going to add a calculator page if you don't already have a calculator page open. So we want the inverse cosine. Was it the inverse cosine? Aw, man. No, it's the inverse sine, my bad. So inverse sine. And we're typing in negative 2 divided by 3. So negative 2 divided by 3. And I'm going to press Control first, then Enter to give me a decimal value. And there's negative 0.72972 something something something. And that's what we'll go ahead and write down in the paper. X equals negative 0.72972 something something something. So this keeps on going. That's a random pattern. That's because it's an irrational number. So that's what the calculator gave me. Now, if you saw the video for 7.5 yesterday all the way through, you understand that inverse sine is defined to spit out an answer between negative pi over 2 all the way up to pi over 2. So it's the right half of the circle, but the bottom half of that half is a negative set of numbers. So what it's giving you is this angle from here to here. Negative 0.7297 is what it's giving you. Problem is that I have to report the answer between 0 and 2 pi. It has to be a positive number, no bigger than 2 pi. And if you remember, 2 pi is 6.28 something something something. So it has to be a number between 0 and 6.28 something. So this answer is unacceptable. So what do? Do I give up? I don't give up at this point. I can actually find out what the answers are that I want by taking that as an absolute value and adding it here. So this is going to be the size away from the x-axis on this side. 7297 something something. And I'm going to add that over to this value, which is pi. So one of my answers, x equals to pi plus 0.7297. And we remember, pi, if you plug it in the calculator, it's about 3.141 something something. Keeps on going. So that's one of my answers, and which we'll go ahead and type that into the calculator right away. So there's a pi symbol on my calculator, pi plus this number, and I got to change the negative because it gave me a negative and I just copied and pasted. So I'm getting 3.871 something something something. So that's one of my answers I box. That's what this one is. So this one here, all the way through, when you erase this, all the way through was 3.871. That's one we box. So what else am I looking for? I'm also looking for this angle from here to here. So that's getting a little messy. So from the positive x-axis all the way to this line, we want to find out what that angle is. So that one is 2 pi minus this amount here. So I'm going to subtract that amount here. So minus 0.7297. And hopefully that's easy to see why we do that. Because 2 pi is a full circle. It's a full circle except for this amount between there and there. Negative 7.297-ish. So 2 times pi is what I'm typing into my calculator. And then minus that value that we got initially. And I'm getting... Now that looks wrong. What did I do? Oh, I didn't type it in right. I put a times symbol instead of a minus symbol or a plus symbol. And there we go. I'm getting 5.553 something something, and that's the other one that we want. So the other answer was 2 pi minus 0.7297, which was about 5.553. Keeps on going. So those are all of my answers. This one here, plus those other two. And that's the reason why we had to go through 7.5 to understand the inverse trigonometric functions very well. So if they had, if you had tried solving, you would have gotten the negative 0.7297, and that would have been wrong because it's not living inside the interval it's supposed to live inside. Something between 0 and 6.28. Both of these numbers were between 0 and 6.28. And that's it for number 3. So that's a really kind of tough problem. They don't get much tougher than that, especially the ones that I'm going to give you in the homework. If anything, they'll look like these, but I'm not going to give you too many of these. So look at example 4 and then example 5. So they just get a little bit tougher, and I'm actually minded to skip over some of these. I might not want to give you any one of them with the quadratic formula. I'll show you how to do them anyway, just in case, because I'm not about to do all of the homework problems to check to see if they're having to use the quadratic formula. So we'll go over number 4 and then number 5. So for number 4, find all solutions of cosine x times cosine x plus 2 equals to 1. Your very first step, you solve the equation cosine x plus 2 equals to 1. Now, because that's nonlinear, you're not going to be able to solve for x or cosine of x by simple subtraction, division, multiplication, addition. So what we do is try another route. Let me expand this to see if we can get a bunch of terms. That's going to be cosine squared x plus 2 cosine x equals to 1. Or what you could do is you can also subtract the 1 on both sides, and it's going to equal to 0 just to get that done already in one step. And this one's not going to be factorizable. And the reason being, that's a 1 in front of the cosine squared. So you want two numbers that multiply to give you -1, and they add up to the middle number, which is 2. Are there numbers that when I multiply them I get -1, but they add up to 2? Yes, there are, but not whole numbers, not integers. So you could try, but the only factors of -1 that we understand are whole numbers is -1 times 1 and 1 times -1. That's about it. And in neither of those cases do we get a +2 when I add them. So that's going to fail. This is not factorable. That's why we have to use the quadratic formula like it says in the problem stem. So quadratic formula, A is 1, B is 2, C is -1. Remember to keep the signs too, so include the signs. So then cosine x is going to equal to, what's the formula? You guys remember? -b plus or minus square root b squared minus 4ac, all divided by 2a. It's one of those things you should still have memorized. So -b plus or minus square root b squared minus 4ac, all divided by 2a. Plug in the values of a, b, and c accordingly. So -2 plus or minus square root 4 minus 4 times 1 times -1, all divided by 2. 2 times 1. Simplify. -2 plus or minus square root, is that 8? Let me double check. My brain kind of sucks at doing stuff like this, so I gotta double check. 4 in the first, and then you have a -4 times 1 times -1. -4 times 1 times -1 is a -4 times -1, which is equal to +4. +4 added to 4 is 8, all divided by 2, so I did that okay. And that square root of 8, you should remember, can reduce to a square root of 2 times a 2 on the outside. Those are all reducible by 2. -2 plus or minus, -1 plus or minus the square root of 2. So that's what we have so far. So then we're solving cosine x equals -1 plus square root of 2. And that is approximately, let's see how much. I'm going to have to go to a calculator for that. -1 plus the square root of 2. 0.4142, and it keeps on going. That's one problem. Another problem. Cosine x is equal to -1 minus the square root of 2. And for that, calculator again. -1 minus this time. And you're going to get -2.4142 something something something. Now the idea is cosine of x has a range between -1 and 1 and is undefined anywhere else. So in this case, since this number is not inside that interval, this one has no solution. So I don't even consider this one. And the reason being, cosine x is supposed to be equal to a -2.4142. What does that mean? Remember, cosine is the x-coordinate, and I'm looking at the circle now. X-coordinates only lie between -1 all the way up to +1. It's only numbers between -1 and +1. If we're talking about cosine equaling to -2.4142, we're talking about a point all the way out here at -2.4142. And that doesn't happen because that's not inside the circle, or that's not on the circle. So that's not geometrically consistent with the unit circle. So that's why we say there's no solution to this thing. So we're only going to consider the first one as something that contributes viable solutions. Okay, so going back to it, cosine of whatever angle we're looking for is equal to 0.4142-ish. So that's an x-coordinate because cosine is an x-coordinate. X-coordinate of 0.4142 ... We're looking for points on the circle with that x-coordinate, and there's 2 points on the circle with that x-coordinate geometrically, here and here. So what we're looking for is the angle this way, from here to here, and then the angle this way, from here all the way out over here. And why all the way out over here? Because they didn't tell me. Find all solutions. So crap. What does that all mean again? That means all of them. There's an infinite amount of them. So I'll have to figure that out in a little bit. But so what I'm going to do is I'm going to worry about, so if you don't remember, example 1. Let me go back to example 1. For all solutions. And for all solutions means we need to have something that looks like this with a plus n times something involved. So that's going to be involved. And I'll worry about it later. Let's find just the part A stuff, which is where we're only finding the primary circle values. And let's look at how we're going to figure those out. If you remember, inverse cosine, so x is going to equal to the inverse cosine of 0.4142 ... keeps on going. I'm going to move this further down because I'm going to need some more space here. So we're going to plug that into a calculator. And if you remember, cosine inverse is programmed or designed to only give values in the top half of the circle. So it's only going to give us something between 0 and pi, between 0 and 3.141 something something. So I'm going to go to my calculator, which I might edit that back in there. And I get 1.1437 ... keeps on going, radians, because my calculator is currently in radians. So this value here, 1.1437. And that's one of my answers. So I'm going to box that. I'm going to underline that or something. So I'm going to write that down over here somewhere, wherever I can. X is equal to 1.1437. Oops. How do I find the other one that's still in the primary circle? So I want to know what that is between here all the way out that way. And how do I get that done? So the way to get that done, one way, is to take the value that we got and subtract it from 2 pi. So from here to here, this is 1.1437. The whole way through, though, is 2 pi. So I'm going to subtract this piece off of it, and that's going to give me the one that I want. So what that looks like is 2 pi minus 1.1437 ... So let's try that. 2 times pi button, and then minus this number that I got from cosine inverse. And I'm getting 5.1395 something something something, keeps on going. And that's the other one that I wanted. That is 5.1395. So if they weren't just asking for all solutions, they only wanted it between 0 and 2 pi, this is it. How do I find the rest of them? So the rest of them, these two don't differ by 180 degrees, so I can't use that same cheat or hack that I used for the first one, where I keep adding a multiple of 180. So the way to do that though, so the workaround, x equals to 1.1437. I'm going to generate more of those only, by adding integer multiples of 2 pi. So obviously if I go an extra 2 pi this way, I find another. And if I keep on repeating that process, you'll keep on finding more. So that's one of them. The other one is 5.1395 plus n times 2 pi. That's the other one. So this right here is the actual solution that they want. That's for all values of theta. And that's it for example 4. So that one's really ugly. And that's ugly for several reasons. One of them is that this is an equation that I can't solve by factoring, so we had to go with the quadratic formula. Quadratic formula gave us two answers, -1 plus minus square root of 2. One of those answers contributed no solutions whatsoever, because it was outside of the range -1 to 1. The other one corresponded to a value that's not on one of the special unit circle values that we understand very well, so I had to resort to going to a calculator to find out some extra information. And the information we found out was one of the angles, 1.1437, and we used that to generate all angles that satisfied this property. There's quite a bit of stuff there. We'll look at the last one, example 5, which hopefully isn't as bad, but it might be. So we'll see. Solve cotangent x minus square root of 3 is equal to cosecant x over the interval 0 to 2 pi. So not as bad because it's restricting us to just the main circle. So cotangent x minus square root of 3 is equal to cosecant, and they're telling us what to do. I underlined it here. They want us to square both sides. Now if you remember, you're allowed to square both sides to solve for solutions of an equation. Problem is squaring both sides is going to produce extra answers that are not solutions to the original equation. However, everything that solves the first equation will solve the squared equation. So squaring is going to produce all answers of this equation. However, it's going to produce some extra stuff, extra crap that we got to check and throw away. So we square both sides. So we're going to solve this equation instead with squaring both sides first. And to square the left-hand side, perfect square, it's a shortcut. Cosine squared x minus 2 square root of 3 cosine x plus 3. Right-hand side, it's already done. How do we get this? That I'm not explaining. That's a perfect square, so it's a shortcut. If you want to see if you can figure out how that works, you take this one, multiply it with itself, FOIL, combine like terms, and you should get the same thing. Okay, so cosine squared minus 2 square root of 3 cosine x plus 3 is equal to cosine or cosecant squared x. And if you analyze that, there's quite a bit of, oh, and I did something wrong here, did I? Some of you already saw it from the get-go and got annoyed probably because I kept on going with it. This is cotangent, not cosecant. That scared me a little bit when I saw cosines. That didn't seem right. So those are cotangents. And now that makes it a lot easier for me. Why does that make that easier for me? Because I can rewrite a cosecant squared in terms of a cotangent squared. If you remember, cosecant squared is the same as 1 plus cotangent squared. That's just a Pythagorean identity. So that's Pythagoras number 3 is usually how we order that. So cotangent squared x minus 2 square root of 3 cotangent x and then plus 3 is equal to 1 plus cotangent squared x. A nice thing happens here. The square terms will cancel each other out if you subtract cotangent squared on both sides. If we subtract 1 on both sides, you get -2 square root of 3 cotangent x, what is that, plus 2, equals to 0. And then what next? Maybe I should have moved the 3 instead of the 1, because I'm going to have to move this 2 back this way. Oops. -2 square root of 3 cotangent x is equal to -2. Then you divide -2 square root of 3 both sides. These cancel. Cotangent x is equal to, well, I can cancel -2's, and you're left with 1 over the square root of 3, which is also square root of 3 over 3. So then we got to find out what angles make this expression true. Okay, so cotangent is square root of 3 over 3. I can ignore the square root of 3 over 3 and just change that to tangent x is equal to square root of 3. So I'm going to erase this, and I didn't need that. So I'm going to change it to something I understand better. I understand tangent better than I understand cotangent. So tangent we'll say is square root of 3. Square root of 3 came from reducing square root of 3 over 2 over 2, or square root of 3 over 2, divided by 1/2. And the 2's cancel each other out, and you're left with just square root of 3 over 1, which is square root of 3. That's square root of 3 over 2 and 1/2. Those are cosine and sine, or sine and cosine respectively, for the same angle, and that angle is 60 degrees, or, because it's in radians, pi over 3. So that's sine pi over 3, cosine pi over 3. So the angle that we're looking for, one of them at least, is pi over 3, probably. It's possible that's one of the answers I have to throw out, because what you have to do, since we squared both sides, the answers that we get might be extraneous, and I have to plug them back in to check to see if they work. So pi over 3 is one of them, hopefully, and I'm going to draw where pi over 3 is at. It's supposed to be a 60-degree angle. Tangent is positive square root of 3. There's only one other place where tangent is also positive square root of 3, and that's this angle. From here to here. That is 4 pi over 3, I think. Let me double check. That's 1, 2, 3, 4, 5, 6. Yeah, so it's 4. So 4 pi over 3, because I'm forgetting my unit circle, basically, is what's going on. So there are those two angles. 4 pi over 3 and pi over 3. Those are the only two that I'm seeing produce anything meaningful out of this equation. Now, I couldn't box these because I have to double check to see if they're correct. And that's going to take a little bit of time to do. So what I got to do is I got to check the original solution, or the original equation. The original equation is cotangent x minus square root of 3 is equal to cosecant x. So we're going to check both solutions. X equals to pi over 3. So when x equals to pi over 3, you plug in pi over 3 for cotangent, and you're supposed to get square root of 3 over 3. Minus square root of 3, and that's where this is going to hurt. So I have to subtract those two. If I subtract those two, we think of this as square root of 3 over 3 minus 3 square root of 3 over 3. That way those 3's cancel out and you're left with just square root of 3. But you leave those 3's the way it is, and you're going to get -2 square root of 3 over 3. Is this equal to cosecant of pi over 3? That's the question. So what's cosecant pi over 3? It's the reciprocal of sine of pi over 3. So 1 over sine of pi over 3. Sine of pi over 3, I'll write it up on the top over here. Sine of pi over 3 is equal to square root of 3 over 2. We want the reciprocal of that, 2 over square root of 3. And we need to rationalize that, which is 2 square root of 3 over 3. So we have 2 square root of 3 over 3. Is that matching up with -2 square root of 3? Where to get the negative from? That was by subtracting square root of 3 from square root of 3 over 3. So we have a negative quantity equals to a positive quantity. They only differ by a negative sign. And that's the reason why there's extra stuff. We squared both sides. So what we're doing is we're adding those extra possibilities where they only differ by a sign. We don't want them to differ by a sign at all. Or we don't want them to differ by a sign. We don't want them to differ by anything at all. So no. this x equals to pi over 3 has to get thrown out. So then I got to check this all over again. But for x equals 2 pi over 3, oh no, not 2 pi over 3, 4 pi over 3. So does it work? So what I'm doing is I'm plugging in cotangent 4 pi over 3 minus square root of 3. So what is cotangent 4 pi over 3? Well, that's also square root of 3 over 3. That was the whole point behind this exercise, solving for these angles. So both those are both angles for which cotangent is equal to square root of 3 over 3 minus square root of 3. That is again negative 2 square root of 3 over 3. So, there. This is supposed to be equal to, so we don't know if it is, cosecant of 4 pi over 3. So we'll double check. Cosecant of 4 pi over 3 is 1 over the sine of 4 pi over 3. So sine of 4 pi over 3 is the y-coordinate at this point. So that is going to be, this one is 1/2 negative square root of 3 over 2. So it's negative square root of 3 over 2. We want the reciprocal of that, so it's negative 2 over the square root of 3, which is negative 2 square root of 3 over 3. And these two match. So this is a check mark. They are equal. So that means the 4 pi over 3 works. But the other one didn't work. So the only answer in this case is the 4 pi over 3. And the reason being, it's because cotangent ended up being negative. We wanted where cosecant was also negative as well. And cosecant is not negative in the first quadrant, but it's negative in the third quadrant. And that's the ugliest type of problem you'll see for this particular section. Also for the chapter, in my opinion. This is the hardest part of the chapter, I would say. So that's going to be it for this section. That's going to be it for the chapter. You will have a homework assignment for 7, 5, 7, 6. That's going to be due this Friday. And that'll be it.